Welcome everyone to the Committee on Geotechnical and Geologic Engineering webinar series. My name is Marty McCann. I'm the current chair of CAGA, as we refer to it. Before we start, I just wanted to thank our staff for helping put on this webinar and our webinar series. Sam Magsino is the director of CAGA. She's a member of the National Research Council staff, and Remy Chapada, who's the staff administrator who makes sure that all of our tech is working. I'd also like to thank our committee members, Professor Pedro Arduino from the University of Washington, and Ms. Jamie Dwyer, who will be assisting today with moderating and presenting our webinar. And so with that, I'd like to turn it over to Pedro, who will be the moderator. We'll tell you a little bit more about the particulars of how the webinar will run, and we'll introduce today's speaker on biogeotechnics. Pedro?
Thank you, Martin. Good morning and good afternoon, everyone, and welcome. Thanks for joining us today. As Martin indicated, my name is Pedro Arduino, and I am a member of the Committee on Geological and Geotechnical Engineering, also known as COGE. I have the pleasure of serving as your moderator for today's webinar on bio-mediated processes and bio-inspired ideas for geotechnical engineering. Jamie Dwyer, another member of COGE, will be helping organizing and collecting the questions and answers, along with Michael Gomez from the University of Washington and also Alejandro Martinez from UC Davis. We are really delighted to have Dr. Jason DeJong that can join us. Before turning the microphone over to Jason, I want to review how you can provide questions. For us, this is important. So to ask a question, you can use the question and answer box, which you can locate by hovering your mouse near the bottom of your screen. You should see a button that is labeled Q&A. Please type in and send your questions there rather than in the chat feature. You can send your questions at any point during the webinar, and I encourage you to do that during the webinar. We are pleased to have so many of you interested in this webinar, but also keep in mind that we won't likely be able to get to all of your questions, though we will try to do our best. Should you have any technical issue, please also use the question and answer features. Additionally, any conclusions or recommendations provided by Dr. Young are his own and should not be thought of as recommendations from the National Academies of COGE, so this is just a disclaimer that I need to add. With that said, let me introduce Jason, Dr. DeJong. So Dr. DeJong is a professor at the University of California, Davis, and a pioneer of biotechnics. He directs and coordinates the research through first the NSF ERC Center for Bio-mediated and Bio-inspired Geotechnics with Arizona State University, Georgia Tech, and New Mexico State University, also through the UC Davis Soil Interactions Laboratory and the UC Davis Center for Geotechnical Modeling. Results from his research program have been disseminated through more than 200 publications. Dr. Young also actively engaged with industry in implementing research advancements into practice. His ongoing research ranges from fundamental microbial science to industry collaborations for field implementation. Dr. DeJong received his Bachelor of Science in Civil Engineering from UC Davis and his Master's and PhD from the Georgia Institute of Technology. Jason is a dearly friend of mine, and I have a ton of respect for his research. With that, I pass the podium for you, Jason.
Good morning and good afternoon, colleagues. I appreciate deeply this opportunity to present on the field of biogeotechnics, looking at bio-mediated processes and bio-inspired ideas for geotechnical engineering innovation. Over the last 20 years, it has grown from a wild idea into one of the most active research areas in the field of geotechnical engineering. Before we move into the presentation, I do want to acknowledge up front the large group of collaborators at the University of California, Davis, and also certainly the Center for Bio-mediated Geotechnics, of which I and UC Davis are fortunate to be a part, along with Arizona State, Georgia Tech, and New Mexico State. And I've also had some ongoing collaborations with groups or individuals at a few other universities as well. So over the next 35 to 40 minutes, I want to walk through the following outline or overview. I want to introduce the topic, first of all, the vision, as well as what the needs and the priorities are for this. From that, build into a sustainability-driven approach that we are using to guide the research in this field, to have one eye looking on the developments, the other eye looking forward. Talk about 3 bio-mediated processes, 3 bio-inspired processes, and then close with a summary and looking at some opportunities and priorities as we move forward. So with that, let's get into the introduction, speaking on a couple different topics. First of all, long-term vision. You saw this cartoon that I had sketched up as part of the advertisement, and what you see and what your takeaway is that there's a lot of systems or solutions here that we don't currently have, and they look a little bit different and a little bit unique. And that those attributes are driven by using either bio-mediated or bio-inspired processes. I would say as a whole, the vision really is that the field of biogeotechnics is rooted in a hypothesis that if we study, understand, harness, translate, and apply both geotechnical, biological processes and ideas, we can stimulate innovation and generate new geotechnical technologies that in the end can produce step changes with respect to our practice, and from there deliver advances with respect to sustainability, performance, safety, and ultimately societal well-being. Up front, I want to define and distinguish between these 2 different modes. The first being bio-mediated processes, which began roughly 20 years ago by a few of us around the world. And this really focuses on the initiation and regulation of natural biogeochemical mechanical processes to produce changes in soil engineering properties. More recently, in the last 5 to 10 years, the concept and process of bio-inspired design has come to the fore, and this is the abstraction and translation of natural biological solutions in terms of either forms, behaviors, principles, to develop new solutions to engineering challenges. So first, if we look around us, we see creativity in nature in many different places, and we realize that these different organisms and processes have been doing geotechnical engineering for a long time. They have different processes in which sensing and penetration have become very efficient. Tunneling has been occurring for an extensive period of time by different organisms. Foundations and anchorage solutions are developed for almost all of different plant species. There are natural processes to diffuse energy and to provide coastal erosion or river erosion resistance or prevention. Compaction is a process used by animals as well as biocene construction. And there's a variety of different processes which naturally cement soils together, which is an alternative for what we do. So at a high level, I think we could argue that the creativity that's evident in nature can constitute an alternate source of innovative solutions from which we can gain inspiration, and we can abstract different kinds of ideas. Let's look at this a little bit more closely. First of all, looking at nature's solutions, and we would see that nature designs are ecosystem specific. We also have to remember or appreciate their objective, which is primarily survival and reproduction. The currency that they make decisions by is the materials available and the amount of energy they have to survive and to grow. In almost all cases, they are multifunctional systems. They have to serve more than one purpose for it to be a successful endeavor for an organism. Built into that is the idea of the continuous reuse or cycling of the materials that are available and at hand. They can adapt to growth and adapt to demand and with growth, and they often can be self-healing. If we lay this up side by side against geotechnical engineering, we see in some ways we're similar. We do project site-specific design. We're concerned about safety, but money also drives us, the capital cost in terms of our currency. Historically, we've had a lot of single functionality in our applications, but that increasingly is becoming more multifunctional. From a sustainability aspect, we largely do once and done type of construction that is not necessarily adaptive, and certainly it's not self-healing. So at a minimum, we have to appreciate that the solutions in nature have a similar and even greater constraints in their designs than we have in geotechnical projects, and therefore we should be able to extract some insight from them. So creativity is the first takeaway. Second thing that we need to think about is the type of loading and the magnitude of loading that we're continuously designing for now. And in many cases, a variety of either rapid or very slow type of hazard events are dictating the designs for the geotechnical systems that we apply. Munich Re is a reinsurance company, and annually they plot worldwide the primary or the largest natural disasters with the greatest consequences. And flipping through a couple years of these types of impacts in 2016, in 2017, in 2018, and in 2019, we can see that the exact type of event or frequency of the event differs, but in all cases, in the United States and certainly around the world, these events are continuous, they're significant, and they're affecting our society. And we have to consider these increasingly in design. And so we are really asked to be designing for higher and higher performance demands because the consequences are more severe. So the demand component of our design is increasing. This is somewhat challenging because we also have to look at how we're building and how construction is currently going on. The construction industry in combination constitutes about 75% of all raw material use, 55% of all fuel use, and the manufacturing and production of concrete, steel, and aluminum constitutes about 22% of greenhouse gas emissions. So over the course of time, essentially post-World War, all the way up through today, aside from a few financial crises, we have been steadily increasing the amount of construction materials used at a non-sustainable rate. Further, as we have become more industrialized, the amount or percent of renewables that we use has been declining steadily. So we have a challenge in this aspect as well, that our current construction practices used to build geotechnical systems and other infrastructure use materials and processes at rates that cannot be sustained in the future. Which leads to the third point, and that we need to be building towards a sustainable future. And if we look at the United Nations 2015 goals for sustainable development, they have outlined 17 different goals, which you can easily read online. I'll pass through these, and their descriptions make it clear that what we do as geotechnical engineers arguably have direct impacts on about half or more than half of these, and arguably secondary impacts on the rest. So we have a role to play in the decisions that we make and how we go about design and what type of solutions we use. And so the geotechnical engineering has the opportunity to impact and contribute towards achieving several of these different sustainable development goals. So the question then becomes, from the creativity of nature, from the increasing demands we have from an engineering practice, from the fact that we cannot continue to construct things in the way that we have before, and for society's goal or objective to move towards more sustainable living, we need a framework and a context within which we can be evaluating and guiding research and research development. And this is where this sustainability-driven approach for biogeotechnics innovation came from. This is, as we call it, within the center, the life cycle sustainability assessment framework. And let me outline what this constitutes and how this has been formed. First of all, we have to appreciate that we have a triple bottom line. Our first mandate from Society of Civil Engineers is that we provide safety. The economics require that be at a reasonable capital cost. And so those two we are thinking about all the time, and I think we do quite well. The one that is lacking, I would contend, is with respect to sustainability in the environment. We do environmental impact reports and those types of things, but we don't necessarily look at all the processes and technologies we're using through a sustainability type of lens. And this is really the role of the life cycle sustainability assessment. It's a framework designed to consider the entire system, from extraction of raw materials to construction and through the maintenance and end of life. And the impacts that we quantify come in 3 different areas. The first one is the environmental life cycle assessment. The second one is a cost assessment. Those 2 are rather rigorous in the field now and rather mature. The third one is the impacts to society. But those metrics and the quantitative robustness of that process is lacking relative to the other 2. But nonetheless, we can use all 3 of these different tools. If we apply this to different research projects, the intent or the objective is that it provides and helps with balanced consideration of sustainability-oriented activities. We can identify sustainability-related or driven research tasks. We can also compare the technologies we're developing against those used currently in industry, and those are called business as usual technologies. And we also can evaluate the future as that technology matures, competitiveness with respect to cost, performance, and sustainability. So you can look at the entire spectrum of development from left to right, from a very small scale element tests where we're really proofing concepts, to upscaling and larger validation type tests, to field scale demonstrations, and ultimately to industry using this routinely in the future. And throughout this entire process, we can perform life cycle sustainability assessments of the project, not once, but on some frequent basis, let's say annually. And when we do that and the project is relatively young, we can't do a full analysis, but we can certainly go in and look at the elements of materials and the processes being used and get some early identification of hotspots of what could be costly, what is the feasibility. And as we mature and these projects go to larger and larger scales, we can then start comparing it to existing BAU technologies, and we can also be optimizing for field scale. And there's a component in here to develop tools for industry decision making. Ideally, this LCSA approach would really trigger priorities and identify priorities early in the R&D to realize sustainability related benefits. And if we provide these feedback early and frequently throughout, we'll have an honest assessment of the potential of these different technologies. So I want to draw this out a little bit more with respect to 2 different frameworks. The first is what's called the Culling-Ridge dilemma, and shown by the schematic. On the x-axis, you have the project maturity going from very young to being mature on the right-hand side. You have the potential to reduce impacts. And interestingly, when the project is in its infancy and you're just making early decisions about what constituents to use, what processes to use, you have a high flexibility in order to change and make sustainability related decisions. And as the project matures and you move from left to right, now the technology becomes more locked in, you have less flexibility. And if you want to make change, it's going to come at a much more substantial cost. So we need to be looking at through the lens of sustainability throughout development. The second part is within the Gartner hype cycle, which is often used in technology development, where you have the initial idea generation, you have a peak which of inflated expectations, you fall to the trough of disillusionment, you grow up the slope of enlightenment, and eventually you plateau and it's an accepted technology and practice. The intent and desire of LCSA implementation is that early on we're correcting ourselves, is that we're making a critical, early, honest assessment of what the technology can deliver. At the same time, that should shore us up from the trough of disillusionment that we are continuously reevaluating and not surprised by as much. And eventually you can reach that plateau. So in the context of the priorities we have as society, and in the context of this framework, let's now move and look at some of these different technologies. Bio-mediated geotechnics, we're going to look at 3: biocementation, biogas, and biofilms. All 3 of these approaches, as well as several others that people are developing, are really based off of chemical reactions occurring within the soil. we need a process or the biology to mediate the timing, rate, and distribution for which these occur. And if that is successful, we can realize improvements in the mechanical engineering properties, permeability, modulus, strength, and volume change. And as we do this, and this transformation takes place, we have to be able to monitor that process in real time, ideally. And geophysics is an excellent tool for this. From there, we're moving to field applications, and there are many, and they are quite varied, as a lot of other people have shown. And through that, we have to deal with the upscaling to the field with respect to uniformity, permanence, and byproduct management. So to highlight a few attributes of this bio-mediated process, we're really trying to control and regulate biology and chemistry to accelerate or delay the processes. Process monitoring is key to track progress. The property changes can be substantial. We can achieve different levels of improvement that can be tuned to what is required for a particular site. So it is not a binary improvement. It can be applied very incrementally. We do have challenges with respect to upscaling that are similar to a lot of the ground improvement technologies. And again, the field applications can be wide ranging. So I'm first going to talk about biocementation and spend most of the time on this, in part because this is one of the technologies that has been researched the longest. And today we're collectively going to group together at least 3 plus other methods of microbially induced calcite precipitation, enzymatically induced calcite precipitation, and microbially induced desaturation and precipitation, in this part really focusing on the precipitation. When we apply these technologies, all we're doing in the end is precipitating calcium carbonate amongst the soil particles. So that can occur by ureolysis or it can occur by denitrification. That precipitation occurs preferentially at particle contacts, as you can see here, but you also have some coating on the particle surfaces as well. This has 3 important attributes and contributions to behavior. The first is the binding of a cementitious material between the contacts. The second is your density is going up and your porosity or your permeability is decreasing. And the third is that your particle angularity and interparticle frustration is also increased if you load the soil beyond its strength and you actually break those cementation bonds. That cemented material can still provide some contribution. So these processes have to be regulated, and we look towards microbiology to provide that regulation. And so again, microbiology provides the control of the timing, rate, and distribution of the precipitation. Early on, ourselves and almost everyone in the field would look at bioaugmentation as the way of treatment, where you would inject the bacteria. But through the research of others, as well as ourselves, we have realized and shown that biostimulation of native bacteria is entirely possible, and they eventually outcompete any bacteria that you inject. And so one example of this is how the microbial population changes at the genus level, as sorted by some high throughput 16S sequencing of what the bacterial population or microbial population is prior to treatment or prior to stimulation to what it is after stimulation. And so we have, through environmental stressors, we have the ability to control the bacterial population and stimulate what's needed. So this can reduce costs, environmental impacts, improve spatial uniformity, and certainly eases regulatory permitting. In addition, the process has been shown to be feasible and robust at great depths beneath the groundwater table in saturated soils under anoxic conditions. So we've initiated this process. So the next part then is process monitoring. We need to be able to track what's going on during the treatment. The chemistry and biology monitoring tells us that there is activity, but it does not necessarily confirm mechanical improvement. So that has to happen in real time through geophysics, and in particular shear wave velocity. And after treatment, there's a variety of more conventional tests, including cone penetration, laboratory tests, and direct calcite content measurement. So to show you 2 examples, on the right-hand side is from a upscaling test that we performed. You can see the tip resistance on the x-axis, the vertical axis is depth. Prior to treatment, you have the gray dash zone with about 3 to 4 MPa tip resistance. And through subsequent treatments, that tip resistance goes up to about 25 MPa. So there's a substantial increase in penetration resistance. That penetration resistance right here, QC, can map to the amount of calcite that has been precipitated through the process. And for the real-time monitoring, that calcite content also maps to the improvements in shear wave velocity. So they both track well for us. Researchers have collectively documented the improvement to a whole variety of soils, but here I'm going to synthesize it for improvements to poorly graded sands. This is the area of work that has been performed by a very wide range of researchers from many different places. But in summary, the shear wave velocity can be improved from 100 or really just 5 meters per second up to 1500 meters per second. Unconfined compression strength between 0 to 5 MPa. Peak friction angle increased up to 45 degrees. You can transform a contractive soil to one that is dilative. And the cyclic resistance for a given set of loading conditions, by adding 1% calcite, you can increase the CRR from 0.1 to 0.3, and the permeability can reduce quite a bit as well. So I just want to highlight this with two sets of figures. The first coming from monotonic undrained triaxial test. The black line here is an untreated condition of loose sand. And as you add cementation, you increase the stiffness, you increase the peak strength of that material. And with respect to excess pore pressure generation, initially this is positive excess pore pressure. And then as you add cementation, you make the soil more and more dilative to where you have strong dilated tendency and negative excess pore pressure generation. So a substantial change. Similarly with cyclic DSS tests, if you have an untreated loose sand, you fail within the first cycle for a CSR of 0.2 and no shear wave velocity increase. If you add roughly 1% or 0.5% calcite, that corresponds to a shear wave velocity increase of about 100 meters per second. And clearly the cyclic resistance has moved up substantially. From those element tests, we have to move to the field, which requires upscaling. And in the process of upscaling, there are several priorities. Here's 4 of them: material efficiency, the treatment strategies, how we're going to monitor this process, and the byproducts that we might need to remove. So one example of this is a series of long horizontal columns that was performed, 3.5 meters in length, with various ports along the length to take aqueous samples for microbiology and chemical analysis, and shear wave velocity measurements along the length to track real-time the level of improvement. One of the big concerns was achieving uniformity over substantial distances between injection wells, because that is a driver in terms of commercial costs and implementation costs. And so whether or not we look at it with respect to the final calcite content or the shear wave velocity that will increase, you can see that stimulation of the soil in these columns resulted in a more uniform level of cementation and improvement compared to the augmentation column for the set of controlled conditions that we specified, which were for equal cementation potential based off of bacterial activity. So some of the conclusions for these was that the biostimulation can enable more uniform cementation than augmentation for the same reactivity. 1D treatment can exceed 4 meters plus in relatively clean soils, and the byproducts are able to be removed as well. The second part of upscaling is the mechanisms for failure and how we would design with these solutions in the field. One of these top questions, particularly in California, is the issue of liquefaction and liquefaction triggering. So we examined this through small model tests on the small centrifuge at the Center for Geotechnical Modeling, level ground, saturated, loose sand conditions, a variety of sensors to measure the process of cementation degradation, eventually liquefaction triggering. And if we assemble these results together, we can look at this in the context of the standard liquefaction triggering curve that we use in practice. So here would be your standard cone tip resistance. Vertical axis is your CSR, CRR. And this first curve here is what you'd use in practice in standard for 1 atmosphere. The centrifuge model has a lower average confining stress or vertical effective stress on it of 35. So that's the reference point for our untreated soil. And if we look at all the different shaking events that were applied over different models, The open symbols did not liquefy, the closed symbols did. And if we rough approximate a dashed line underneath that, we can get an idea of how much increase you have in the cyclic resistance. And it's clear that this cementation process has a greater impact on the cyclic resistance than it does on the cone tip resistance due to the upward shift. So from this upscaling process, you next turn towards applications in the field. And this next slide is busy. And that is because there are a lot of people in the United States and in Europe and in the UK that have been applying this technology in the field, particularly in the last 2 to 3 years. And you can see the variety of applications of pipeline, surface erosion, tunnel, soil stabilization, 2 projects actually on liquefaction, even though there's only 1 picture here, columns, slope stability, landslides, coastal erosion, contaminants, and fractures. All of these are worthy of a presentation in themselves, so I encourage you to look at the references from these different authors to dig into it in some more detail. But as we move up through the field scale application, we have to still be keeping an eye on how is our technology improving compared to that which is standard in industry. And so this was evaluated for an ideal level ground site with loose liquefiable materials down to about 10 meters depth. And this was in collaboration with some industry partners. And the results of this for improvements for a blow count up to about 22 from initial blow count value of about 12 to 15. In project costs for millions of dollars in primary energy, you can see these results and the ranges of results for dynamic compaction, vibro compaction, vibro replacement, compaction grouting, and deep soil mixing. The whole objective, of course, as you're advancing and improving your technology, is you're interested in going down to the origin, reduce costs, and oftentimes with that, it's correlated to the amount of energy that's used. For MICP, this technology has been advancing and we are continuously moving down in this space, but we're not done yet. And several different people working on this field have been identifying different ways in which that you can still realize cost savings. And at the same time, you can also realize reduced impacts by using different types of materials. So we have to keep an eye on this space and on this domain at the same time while we continue while these technologies continue to mature. So let's move to the second one, which is bio-mediated gas generation. This process now is the generation of gas bubbles in the pore space, as you can see here, and the particle structure is largely unchanged. It's been shown that stimulated microbes can generate this gas by denitrification, and these bubbles then decrease the degree of saturation and increase pore fluid compressibility, which is amenable to monitoring with compression waves. It has substantial changes in the mechanical engineering properties. One example is shown here for monotonic resistance, where it's a mean effect of stress on the x-axis, the deviator on the y-axis. And if you treat the soil in a 100% unsaturated or saturated condition, you get the bottom line right here. And as you decrease the degree of saturation down to about 95%, you see the behavior and the response change substantially. It's no longer collapsing, and it actually will turn and begin to dilate up the failure envelope. In the cyclic space, the transformation or the improvement is also substantial. Here is your cyclic resistance curve for 100% saturation. And as the degree of saturation decreases only by a few percent, you almost have a doubling of the resistance or the capacity that you have. This process also has been being upscaled to the field. And in that process is looking at 2D planar flow, where you have flow through a sand layer and you can watch and observe and begin to model how the flow regime changes as the gas bubbles are generated and redirects water flow. And application to the field, then you can use P-wave velocity monitoring and can see how initially saturated soils over a period of about 20 to 30 days decreases substantially to some very low value, confirming that the denitrification process is increasing pore fluid compressibility, which can then map to cyclic resistance. The third technology we're going to talk about is biofilms. Biofilms is really a process of, the process is the formation of cells and polymers and solids that attach to particle surfaces, shown schematically right here. Again, stimulated microbes can induce this process. We don't have to be injecting bacteria. And this is an organic precipitate, which is reversible. So this is different from the other two in the sense that when we stop treatment, this will return to ambient conditions, which could be useful during construction. They coat and bridge particles, as you can see below. And when that happens, you have substantial reductions in permeability. So here's a long column experiment. The control column for this is this gray line to the right-hand side. And you can see near the injection phase, the permeability reduction is 2 to 3 orders of magnitude. And as you get towards the tail end, the reduction is approaching 1 order of magnitude. This is one of the primary challenges for upscaling, is how this technology can be applied and be realized in the field in a more uniform manner. Let's turn our attention to bio-inspired geotechnics for the balance of our time. I'll touch on the approach overall. Again, we're now looking at biological systems that we are interested in, but very importantly, we're going to do that through the lens or the eye of the engineering knowledge that our discipline has. We're going to leverage our soil behavior, soil structure interaction, and our system design. We're going to, from there, abstract different forms or behaviors or principles that we can use. We're going to formulate a hypothesis. And we're going to then test that hypothesis using a variety of techniques from the biology fields, from the physics, as well as numerical simulations and experiments. And when we test that hypothesis, we could find that it doesn't work, and we're going to loop back and continue to iterate. We might find promise at the initial bench scale experiments, and we begin to upscale this to the field. And we might encounter challenges at that level once again, and we might loop back and retest this hypothesis. So this is an iterative process without a doubt. But eventually we realize some type of field application with a new design, some way to fabricate a new deployment or installation, or some way to monitor. The key attributes being that inspiration is triggered by the study of biological systems in the lens of engineering knowledge. We can abstract the biological system, and when we do that, that allows a higher order ideas to be extracted and studied. We're going to do hypothesis testing. We're going to be challenged in upscaling across different stress and length scales, but we believe that there can be substantial improvements relative to how we solve problems currently. So let's look at this through 3 examples. The first being tree root inspired anchors and foundation systems. The tree root systems that exist beneath plants and trees provide stability, nutrient, and water uptake. We can look at this through our knowledge of the deformation and capacity of foundation systems. And the idea that we're abstracting is looking at how the root architecture that governs these attributes, how those perform under different combinations of horizontal, vertical, and moment loading. And we believe that the nonlinear root attributes can enable a tunable foundation performance. So here's an example of that. These are root stocks that were pulled from an orchard in a research project, and there's a whole host of different ones pulled. Here's 3 representative load displacement curves. You can see that the initial stiffness, the peak strength, and the rate of softening all differ. And this difference is dictated based off of the root structure. And this is being mapped to be able to control or tune for different levels of initial stiffness, different maximum capacities, and different rates of softening. This was a comparative analysis was performed for these different root systems against conventional foundation design, either on an equivalent mass basis or equivalent volume basis. And if you compare the capacities of the trees in pull out versus a micropile, that is a 10-fold performance in benefit of the tree. If you do it with respect to shallow footings, obviously that improvement goes up and you're looking at about a 50 times improvement. So our takeaway here being there's plenty of room to improve if we deviate from our linear piles that we typically install. This work is being upscaled through other people at the center. And here's an example of that. This is the 3D printed models with 3 different branches at different angles. Load pull-out tests for this. You can see that if you have the highest number of branches at the largest angles, you have a greater capacity, but you also have more softening compared to some other solutions. And using X-ray CT, you can go into X-ray images and sequences of X-ray images and really understand the failure mechanism and understand how these different, the spacing and the length and the angle of these branches affect capacity. The second technology we want to take a look at is invertebrate-inspired soil penetration. And here we're interested in earth and marine worms as well as clams. We're going to examine this through our knowledge of penetration resistance and cavity expansion. We're going to be looking in particular at the motion and sequence, the motion sequence and shapes of invertebrates during their burrowing. And this peristaltic motion provides simultaneously an anchorage force and decreased penetration resistance. We believe this can result in self-penetrating sensors and probes. So here's some of the organisms on the left-hand side. The key part is during this burrowing process, there's radial expansion at one section, which provides a reaction for the penetration of the tip moving forward. This is not too dissimilar from a cone penetrometer fixed ahead of a pressure meter expansive type of device that can handle a reaction type of load. You can do cavity expansion on this, compare it to cone penetration resistance. You can also compare experimental data. And we have found for a variety of different soil types and soil conditions that the length of this anchor relative to the diameter of the penetrometer needs to be in the range of about 2 to 5 in order to provide a sufficient reaction. What's interesting is that that general number is in pretty good agreement with that of different clams that exist in a variety of places around the world. And you can see the length to diameter ratios for these clams. And so the clams are doing it. Why can't we do it through some geotechnical innovation? And so that's what people are doing. Discrete element modeling is being used to model the expansion and the force networks that are generated both during expansion and during shear. You can also look at the tip resistance and if there's a coupling or interaction between those. And there are 3 different groups within the center that are generating model scaled penetrometers with robot type penetrometers that can self-burrow and self-advance. Ultimately, the vision is that you would have scenarios where you can be penetrating your cone or some other probe, have downhole reaction modules, and the requirement of a dead weight of 20 or 30 tons on the ground surface, which is transported to all the different sites, can go away. So the last example for the day, and then we'll wrap up, is snakeskin inspired anisotropic friction for piles. In this case, the interest is really looking at the underbelly of the snakes, which you can see here, and that is different than the scales on the top. We're looking at this through our knowledge of soil structure interface behavior. And the abstraction is that the anisotropic shape of the scale enables bias load transfers. So when the snake needs to react against the sand to move forward, it has a high frictional value. When at the same time, when the rest of the body is sliding forward, that experiences much lower friction. And this has been defined in the biology literature as shearing in the cranial direction, that is against the scales, versus in the caudal direction with those different scales. And the hypothesis is that this anisotropic soil structure interfaces could, for example, reduce installation resistance and increase our pull-out capacity. Colleagues at UC Davis, Alejandro Martinez, have been looking at this with the interface shear device. And monotonically, this is not a surprise. You can see similar initial stiffnesses, but you get higher frictional resistance in the cranial, that is against the scales direction, than you have in the caudal. What's fascinating is this process persists during cyclic loading. So in the caudal direction, you'll get a lower, smaller failure envelope than you can generate on the back cycle with the cranial. And he's beginning to upscale this as well, where you have model piles now of different diameters with lengths between these different ribs or ridges of 6 millimeters performed at the UC Davis centrifuge. One monotonic example of that, testing example of that, is that when you install in the cranial direction, you get a higher penetration resistance than you do in the caudal direction. But when you reverse, that is just the opposite. So if you wanted lower resistance during penetration, higher resistance during extraction, relatively speaking, you could achieve that. So let's come to a close here. Our time is up. just to summarize a few points. The first is that the creative solutions in nature are site-specific, efficient, multifunctional, and stable, and they can be a great source of inspiration for us. The LCSA tool, or something like it, provides a framework where we can consider environmental indicators alongside our standards of performance and cost. And they also help us compare against existing technologies. Bio-mediated geotechnical solutions are ones that harness natural tunable processes that can produce anywhere between, say, a 10 and 10,000% change in different soil properties. And these are being deployed in the field. So it's not a question anymore of, can we do this? We've shown that we can, and now becomes a question of optimization and competitiveness. Bio-inspired ideas are younger, but they can be quite a bit more efficient than what we do currently. And there's new opportunities to develop new solutions, which we can't see yet or haven't developed fully, that could really revitalize different industry sectors. And so in summary, this field of biogeotechnics is still young. We've only studied a small fraction of the different processes and ideas that are out there. And there's certainly more by a whole host of authors that I haven't had time to present herein. And it's probably likely that we haven't found the most important solution yet. So there's a lot to be discovered. So before I take questions, it's important that I acknowledge my colleagues, the other faculty members that I work with, as well as the graduate students and research team at the University of Davis. Certainly colleagues at other institutions that I've collaborated with over the years quite closely. The Center for Bio-mediated Geotechnics, which is led by Ed Kavazanjian at Arizona State, as well as Rosie Krasmelnik-Brown, David Frost at Georgia Tech, Paolo Bandini at New Mexico State, and the whole crew of folks there. This process and this journey began about 15 to 20 years ago with the organization of a few workshops in bio-mediated, and more recently a workshop in bio-inspired. And certainly the conversations and the collaborations and the network of people from those has been very, very important. And finally, the funding through the National Science Foundation for this work, particularly through Rick Ferghese, and also Geosyntex Consultants has been a steady partner in this. So with that, going to wrap up here, and I'm happy to take questions. Thank you very much.
Okay, thank you, Jason. Excellent presentation. For the audience, please remember, if you have not already sent a question, you can use the Q&A box, which you can locate by hovering your mouse near the bottom of the screen. Please type in and send your questions there, and we will try to look at those. So here, Alejandro and Jamie and Michael have been collecting some questions for you. So I will try to go through them, some of them. Let's see what happens. So one of them says, what are the mechanisms for improvement for biocemented soils? For instance, friction and changes and cohesion changes. So what is the mechanism that makes this improve?
All right, at a particle scale, the improvement can be conceived or conceptualized by generating rigid cementation between particles, as you can see here. So this can be realized in two different ways. This can be realized as the cementitious bond, which could increase the cohesive intercept. Brina Montoya and others have shown that that can be the case. At the same time, that can also be captured as an increase potentially in the peak friction of the material. You have different ways that you can, if you will, capture or decide to model that. And that's also evident here. Depending on how you interpreted these results and plotted them up, you can see that the peak strength is going up substantially, as well as the stiffness. The critical state strength, or the constant volume strength later on is changed less so.
So good. Here they were also asking, is there an effect of depth, that meaning pressure, on the effectiveness of the biogas soil improvement?
Yes, for biogas, let me slide over to that. The size of the bubbles will vary with the hydrostatic water pressure. And so that obviously has to be in equilibrium. So as you go deeper, then the size of the bubbles will be decreasing. This is something that was observed in the centrifuge modeling. It's something that has also been simulated in the laboratory. Some of the earlier work was Carlos Santamarina, and more recent has been with Leon Van Passen and others at Arizona State University. And so you have to be mindful of that when you're generating the gas in situ, and being realistic in what degree of saturation is achievable based off of the overburden stress and the pressure that can be generated.
So let me see, I have a couple of, how exactly does the biostimulation of bacteria work? Does it involve modification in the environment or addition of nutrients? Briefly, can you go through that?
Yeah, so the general process of stimulation of bacteria, stimulation of native bacteria, is something that has been well known in the microbiology field, which I am not. I'm a geotechnical engineer, not a microbiologist. But the base knowledge for that is quite substantial. There are two options. The one option is you can provide a variety of different sources, including organic carbon and some oxygen, which can be generally favorable for bacteria growth. The catch with that is not all bacteria that exist in the subsurface are the ones that are amenable to either the denitrification process or to the ureolysis process. And so as a result, a general stimulation approach can either take longer to go into effect, or it might not be active in the end. In addition to that, level of environmental stress are so that they are favorable to the bacteria genus that you're interested in stimulating to be successful and to outcompete the other native bacteria. And so there's a variety of publications, some of which are listed here, Burbank and others have done as well, where people have tracked how the bacterial population can change and what are some of those different approaches. There's another paper by Burns that has done this also.
Here there is one. Are there any field implementation case studies on biogeotechnics, and what are the limitations of this technique approach to implement in the field?
So this is the slide intended to kind of summarize where that is at. All of these processes have been performed in the field. I would say for biocementation has been performed most extensively. For biogas generation, there have also been a couple of applications for that. When you move to the field, you have some of the same challenges that you have for some of the ground improvement methods, and really for a lot of geotechnical design. And those would include spatial uniformity of the soil and the material that exists. And so if you're trying to apply these different treatments, you want them to be delivered uniformly in the subsurface, but obviously variations in layering or variations in silt content, for example, could change the permeability. There have been a variety of different tests that by ourselves and other researchers which have shown that if you sample soils from the field, you are able to stimulate native bacteria to do these processes and to facilitate these processes. So that has been shown repeatedly, so that it's not a question of, at least as far as it's been shown, it's not a question that is the bacteria there, but rather the bacteria is there, it needs to be stimulated, then it can facilitate the process, and then you can realize the cementation and the desaturation that you're interested in.
Yeah, related to that, and we are coming to an end here, but there are several quite good questions here. Can you comment on the permanence of the bio-mediated geotech applications? For example, how long will biogas bubbles remain in the subsurface, or how long will the cemented soil particles last? So can you lose the benefit here?
Yeah, so let's take these in reverse order, actually. Very briefly, for the biofilms, the biofilm is an organic precipitate, essentially. And so once you stop treating the system, and if you begin starving it, the bacteria or the microbes will go after the EPS, and the rest of that is consumed. And within a period of a couple of days to a couple of months, you'll return to pre-existing conditions. This could be looked at as very favorable, in that you could be looking at a dewatering system during, let's say, the excavation phase of a building. And when you're done, you stop treating the system and you return to the ambient conditions. And that's much more desirable than leaving, let's say, a permanent cement-based solution in the ground, even though its function is now over.
Yeah.
For the biogas system, one of the attractions of the N2 gas is it has a much slower dissolution than other gases in the ground surface. There is some research out of Japan and other places which have shown that those bubbles can last for decades, on the orders of decades. And when you go to the biocementation process, once the cementation is in place and it has been formed, something like this, it is now essentially a chemical permanence question. The bacteria and the microbes really don't have a role to play as much. And now it comes down to the aqueous chemistry. It comes down to what the base level pH is. So certainly if you had a very, very low pH type of environment, you could have reversal of this process. Mm-hmm. If you have neutral pH or high pH, particularly in more alkaline conditions, all that's favorable for long-term permanence.
So one last question before we really close here. What is the main factor limiting commercial application of these technologies at the moment, and how will this be solved? So quickly, that's a tough one, I think.
Yeah, I would say for all of the technologies, one of the challenges we have is, as a practice, we are very slow to adopt new technologies. We are very hesitant. We talk with a lot of different groups and entities, and they're very happy to be second in line. They don't necessarily want to be first in line. And so as I've hopefully convinced people, some of these technologies are ready and in the waiting for engagement and partnering with industry to be implemented in the field. So that's certainly part of it. What comes along with that is developing the QA, QC procedures, verifying the treatment plans and the methodologies for the field, and in some cases, also following through and ensuring that there's removal of byproducts as well.
So I think that we have reached the time that we had allocated for this. We can continue a little bit longer, but I just need to do the wrap up and then indicate that we can continue a little bit longer with a couple of more questions. So before that, I want to mention that we're approaching the time, the end of the hour, and I want to thank Jason for their excellent presentation and this great audience for your engagement. First, if you have questions about COGI, including ideas for topics you would like to see covered in our ongoing webinar series, please reach out to San Maxino with the email that is going to be on the screen. I will note that the presentation and audio recording from today's webinar will be posted within 7 to 10 days on our website. Please watch your email for announcements about future webinars and events. So thank you very, very much, Jason. And if you want, the audience would like to continue, we can ask a couple of more questions. I just wanted to make sure that we completed what we said that we were going to do. So Jason, do you have a little bit more time to stay around?
Yeah, no problem.
So let's see if I have a couple of more questions that I've been collecting through several media here. For the bio-inspire here, I have one. How do you go about finding biological models for geotechnical systems?
The process of bio-inspired design as a field is actually relatively new. It's only in the last 15 years or so where there has been some structure developed to this. The reference I'm highlighting down here at the bottom right by Helms out of Georgia Tech is a good one to take a look at to understand this. In that it has been, they identified two different processes, which we've kind of wrapped up together in the flow chart you're looking at. One is looking at it from a problem-based system or inquiry, and the other is from a solution-based. So we take a solution-based system, that would be a biologist looking at something, examining nature and saying, this organism can, or this bird can penetrate the water really, really fast, and it has no trouble doing so. That's an interesting thing. Let me abstract kind of that form and that process. And now let me go around looking for a solution for it. And then they have to talk with other engineers and they find, okay, well, would this work for you? Would this work for you? And there's kind of a matching process that goes on. The inverse of that is someone in the geotechnical side, let's say, who has a problem or has a specialty area of theirs. Then they need to go backwards, essentially, and start digging through biology to find what solutions are matches. So this brings up two important parts. One is it inquires interdisciplinary work or interdisciplinary research, where there is a biologist who understands the phenomenological processes in natural systems compared to, and they talk with geotechnical engineers who have problems. And so that's the general process for this. So it takes teamwork, takes an interdisciplinary group of people to work at it. And the reference of Helms is a good one to study that in detail.
So related to that, how do you assess that the solution that works for a small animal that lives in a shallow zone will work for a geotechnical system? There is a scale problem here.
That's absolutely correct. And that cannot be presumed to be possible or be presumed to be the case. I think this is a good example where we can combine what we've observed in biology with some of the analysis tools that we already have to test the feasibility. So we can test the hypothesis. We can actually go in, if we wanted to, we could go into the biology field. And I think we could add to the conversation that biologists are having of how does this mechanism work? Because the processes of cone penetration resistance or penetration resistance to soil is something we have pretty reasonable solutions for as a community. And similarly, the cavity expansion solutions, let's say for a pressure meter, we also have reasonable solutions for that we could share. So we can, first of all, as engineers, go into the worm biologist world or the clam world and bring the mechanics understanding that we have and be able to explain why these natural systems work. And then at the same time, we also know that the cavity expansion and cone penetration solutions have been shown to work for the conventional work we do at greater depth.
Yeah. So
to run an analysis to determine what its feasibility is. And so this is a good example of where that is true and that can be true. There are other processes and mechanisms out there which would have some limitations particularly with respect to stress levels and stress scaling as material properties change.
So, you know, Jason, I particularly have nothing against spiders and ants, but sometimes I don't like to have them around my house. In particular, I don't like to see tree roots near my foundation. So any environmental or public safety concerns related to this biotechnology?
I would differentiate between the bio-inspired and the bio-mediated. And the bio-inspired is just a different shape than what we've been using, or it's been a different process than what we've been using. But there's no particular reason why it would be different or why it would necessarily be harmful. With respect to some of the bio-mediated processes, I think part of the reason that we might find this disruptive or shocking is because it's something different than what we do normally. But I think as a society, we're largely ignorant of what current technologies are doing to the subsurface with respect to permanent increases in pH change or with respect to other types of contamination. And so it's more of an awareness and a perception and a change which stimulates concern. That is the fact that these processes are actually really that different, and in particular, potentially more harmful than some of the existing solutions that we're using.
Yeah. So one last question I have here, now that you have that slide there in the screen, it seems that bio-inspired penetrometers look very attractive in terms of potential to reduce the capital and energy required to collect information. But the question is, how far away is a commercially viable bio-inspired penetrometer? And this is not related only to the cone, but to all these things. How far are we in time to have these things available?
Well, part of it is we have to be realistic. And the other part of it is that these technologies are rolling out over the course of time. The biocementation work, for example, began 20 years ago. Improvements happening quite frequently on an annual basis, and hopefully that continues to grow. The bio-inspired ideas are a decade plus behind in terms of where they are in the research trajectory. So that said, in the next 3 to 5 to 7 years, I fully expect that we'll see some prototypes of this at the field scale that are performing at the stress levels of a lot of our geotechnical projects, which is down to, let's say, 10 to 15 meters.
Okay. So Jason, we are really over the time that we allocated for this. I just really want to thank you for your presentation and the willingness to stay a little bit longer to answer more questions. And again, we still have 171 participants listening to you. And so I want to thank also the audience for its great engagement. So I think that this concludes this webinar. So thank you everybody for your participation, and looking forward to the next webinar from Cogi. Thank you very much.
Thank you.